that, I would like to hand over back to Simon, who is our committee chair, who will do a short introduction to this evening's speaker. So, Simon.
Well, welcome everyone to this event tonight. We're very pleased to have Duncan Bourne with us. Duncan is an engineer interested not only in Elekta and particle accelerators, etc., but he's also a member of the Heritage Group on the IMechE. He's told people about that earlier on, and he's also a mentor. Duncan started his life at the famous Hatfield Polytechnic. It's now the University of Hertfordshire, which I think Hatfield Polytechnic sounds far better. And before spending 7 years designing special production equipment for the semiconductor industry. In 2001, Duncan joined Elekta and has since worked on almost all aspects of the mechanical engineering of radiotherapy systems. In 2009, he was part of a small team that made the world's first combined MRI Linac system. I'm not sure what an MRI Linac system is, so hopefully we'll hear about that tonight. And then a project to commercialise this and bring it to market. He's now a principal engineer working on the improvements of all of Elektra's accelerator projects and products. So please join me in asking Duncan to take us forward. Thank you.
Thank you. Right, let's press on. It's a very broad topic, so there's a lot to cover. I'll try and keep it quick. So this is what I hope to cover tonight. How accelerators work and a bit of history of that, what they're used for in industry, and then as you'll see, one of the main uses of accelerators, and certainly what we do at Elekta, is in radiotherapy. So touch on what cancer is, how we treat it, and then the current state of the art of current technologies, and then just touch on the things that are coming next. So you heard who I am, but you're probably thinking who are Elekta. I've never heard of them. So the ones with very long memories might remember MEL, Mullard Electric Limited. That's who we used to be a long time ago, and we made our first accelerator for medical use in 1953. So we're just coming up to our 70th anniversary of that soon. And we moved to our current site there in 1961, which is the picture you can see there, our new headquarters. If you might see just in the background there, that's Astral Towers. That's the roundabout with the big M on it, the corner of Fleming Way and London Road in Crawley. So we've been there, say, since 61. That makes it the longest established Linac manufactured site in the world, as far as I can see. We changed our name to Philips Medical Systems in '89, and then we were bought by Elekta, which is a Swedish neurosurgery company at the time, in '97, and now we're a global accelerator and cancer medical company. So, to the meat, what is a particle accelerator? Well, it, not surprisingly, accelerates particles. And the particles we're talking about are subatomic particles. As it says, they're near the speed of light. I'll touch on that a bit more shortly. So you've probably seen pictures like this before. These are parts of the Large Hadron Collider at CERN, the giant atom smasher. And when you talk about particle accelerators, that's kind of what we're talking about, right? But actually, they're a tiny fraction of the number of accelerators in the world. So you see that little pink slice, that's the LHC and similar. And the vast majority of accelerators in the world are either for radiotherapy, for treating cancer, or in industry, in semiconductor manufacture or materials processing. So it says there, interesting, is roughly 35,000 accelerators in the world. So it's not like automotive numbers, but it's not tiny either. So what's a subatomic particle? For trying to keep this very simple. So you see picture of an atom, and that atom is made up of protons and neutrons in the nucleus and electrons in an orbiting cloud outside. So they are what we're talking about when we say subatomic particles. And what we're going to be accelerating is either electrons or protons. There we go. Proton, neutron, and then those orbiting electrons. So they are all charged particles. Say all, the electron and the proton are charged particles. Now, if you remember sort of basic physics, if we think of an electron negatively charged, if we put a battery across these two plates and put an electron here, that's negatively charged, and like charges repel. So it will be pushed away from that negative plate and it will be attracted to the positive plate. And that's a particle accelerator. It's a very simple accelerator, but that's an accelerator. That's basically what we're doing. We're taking these charged particles and we make an electric field and we pull and push the particle around. So those really old, very simple accelerators, some of these things you might recognize. You have to be quite old to remember a pedoscope, but I think most people remember cathode ray tube TVs. That's a very simple type of particle accelerator. It's firing electrons around and then steering them onto the screen. The pedoscope, there's a couple of our engineers still remember these in Crawley in the 50s and 60s. It was basically a live X-ray generating source underneath your feet, and you put your feet in that hole and then look down through this while getting a massive dose of X-rays into your face. There's a reason we don't have them anymore, but you could see your feet inside your shoes through this live X-ray. So they're, you know, simple electrostatic accelerators, nice and easy to understand. But for getting much more energy and doing interesting physics and things, you need a much bigger acceleration. So Cockcroft and Walton, you might know famous names in physics. They invented this thing, the Cockcroft-Walton multiplier, and it's basically a way of taking AC electricity, and you see this load of diodes and capacitors, and it basically charges the capacitors up sequentially and then discharges them all in series. So it's still a way of multiplying voltage. So then we're still using an electrostatic accelerator, but it's now big voltages. We're talking millions of volts rather than little batteries. Van de Graaff generator, you probably all remember one of those from school. You put your hand on it and your hair goes crazy. That is a static electricity generator, but it's basically doing the same thing. It's making a very high voltage electric field. So you can then take that those charged field, put that in a tube, and you can use that to accelerate those particles. The problem with these electrostatic accelerators is they start getting very big. You see that picture on the side, that's a very big Van de Graaff, and they were bigger than that as well. But you know, you're talking millions of volts. You see here 30 megavolts, and it really doesn't scale. To get more energy and more power, it needs to get bigger and bigger and bigger. So what we end up with is Linacs, linear accelerators. Rather than increasing that voltage to massive amounts, what we can do is have a number of plates and change the phase on that. So rather than just having a plus and a minus and it goes to it, by switching the voltage in phase with the acceleration, then we can get sequential acceleration. So we're basically putting a number of these electrostatic accelerators in series, and that way we don't need these massive voltages. We can do it a bit at a time, and then we can work with rather more normal voltages. So that's a basic Linac, an electrostatic Linac. That's fine, but they are still very big. So the next invention really was to start using RF acceleration. RF, radio frequency, normally we're talking about microwaves. And this is how pretty much all accelerators work today. They don't accelerate with static voltages. They don't use magnets. They use microwaves. And a good way to think of this, you see the picture on the left of the skier going down a mountain. That's like the particle being accelerated by a DC voltage. It's static and the particle is going down that hill. Whereas using microwaves is like a surfer. That surfer's still going down that hill, but the hill is moving. And that's the wave that is the microwave. So the wave is moving and the particle is kind of surfing along on the wave. So what we then get is a cavity Linac. I say this is the most common, certainly in radiotherapy industry. It's pretty much the only kind of accelerator we use. And what we have is basically cavities, as you see, separate cavities. Each one of those is giving an acceleration by filling it with microwaves. So the microwaves are kind of bouncing around in this cavity, and the particle will come in and it will catch that wave like the surfer and get accelerated. And then it drifts through into the next cavity and arrives just at the right time to go and surf on the next wave, and so on. And each time it goes into a cavity, it goes faster and faster and faster. And separating it up like that into individual cavities, it says if you have two cavities, you get double the acceleration. If you try and do it in a single cavity, you need 4 times the power. So that's how we can accelerate particles in a relatively short space. So here's a blurred image from one of our analysis packages of one of our accelerators, and you see all the little particles flying everywhere. So we are injecting electrons here at this end, and these cavities, as I said, are kind of full of microwaves bouncing left to right, right to left. If you ignore the first 3 cells and kind of look here, what you're seeing is a bunch of electrons catch that wave like the surfer and surf through, and then they carry on into the next cell, and then they catch the wave again and surf through, and you see the colors getting brighter as they get more and more energy as they go. And now the interesting thing where physics gets interesting is, I said we're accelerating particles to near the speed of light. Well, we get to as close to the speed of light as we can, around here. So that's roughly 5 megavolts. You get to as close to the speed of light as you can with an electron. But we keep accelerating. And obviously some of these linear accelerators are, kilometers long. So why? Because you can't go faster than the speed of light. So how are we accelerating anymore? And that's where it starts becoming interesting with the physics, and you get into relativity. So as mechanical engineers, we kind of know kinetic energy is half mv squared, but Einstein said that E equals mc squared, and those equations are quite similar. So when you get near to the speed of light, energy and mass become interchangeable. So we're accelerating the speed of the electron up to around here, and from here on, it doesn't go any faster, but it gets more mass. So we keep adding energy in the form of kinetic energy, but it actually increases the mass of the electron, which is a bit weird as engineers rather than physicists, but that's how it works. So we get more and more mass added, more and more energy. So we're looking, our medical accelerators are sort of 6 to 20 MV. CERN is, I can't remember how many teravolts. It's thousands, millions of times more energetic, and that's this relativity effect, the way we're adding mass. So enough physics, because we're not physicists. So cyclotrons, you might have heard of cyclotrons. These are used sometimes in proton therapy. They're very simple to think of. You see the 3 sort of pink images there in the middle. If one of those pink bits is charged and the other one is charged opposite, then you put the particle in here, it'll be repelled by one and accelerated by the other, and then it will turn it back because you change the phase. So you basically got AC on it, and that'll fire it back. And as it gets faster and faster, what happens is it spirals outwards. It keeps getting a kick every time it goes around, but you're now getting acceleration lots of times in the one unit rather than a linear accelerator, which is fine, and you can get very high energies in a small space. But they're not so easily controlled. You don't get the spectrum we like for therapy, but they are used, say particularly in proton therapy that we'll come on to. But the most important thing in the big round accelerators is synchrotrons. You've probably worked out by now that our industry likes trons. Everything's a something tron, but synchrotrons are kind of like a load of linear accelerators, but all put in a circle. That's the way I kind of think of them. So it's not accelerating all the time, but it's accelerating a bit, and then we use a magnet to bend the beam, just like in that cathode ray tube TVs, you use magnets to bend it. So you bend it around a little bit more, and then you accelerate it again, you bend it around a little bit more. And the beauty of it being in a circle, of course, is now it doesn't need to be enormously long, because you can fire it round the circle and then kick it again, and you can keep adding energy at each time it goes round. Well, you know, that's great. So why don't we do that for everything? Why do we use linear accelerators? Why don't we just make little synchrotrons and keep accelerating round in a circle? And the problem is, it says here, why they always end up being so large is what we have is something called synchrotron radiation. And this is, I said we'd finished with the physics, but this is Einstein again. When you change the momentum of a particle at the speed of light, you lose some energy, and that energy is given off as radiation. So every time we bend that radiation beam, that electron or proton beam going around, we lose a bit of radiation, and that, as it says, increases with the square of radius. So if you're going to go to very big energies like the Large Hadron Collider at CERN, it has to be enormous radius, or you'll lose all your energy before it goes round once. So as it says there, we're looking at 4 kilometers radius for the Large Hadron Collider. It's 27 kilometers long, and it has to be that big to get to those massive energies. Most synchrotrons are a lot smaller, but they do end up being quite large so that we don't lose this. That synchrotron radiation is actually quite useful sometimes, which we'll come to in just a moment. So that's summing up basically what I said there. There's a fundamental choice between using a Linac or a synchrotron. The synchrotron's got a lot of advantages, but you get these losses. The Linac is very simple, but it becomes very, very long. Sorry. So now we've seen what accelerators are. They accelerate these particles to very high energies. What do we use them for? Well, most people have heard of those high energy physics things. I say most people have heard of the LHC, but also they're used as light sources. We'll explain what a light source is. Cargo scanning. So at Dover and Channel Tunnel and things like that, they've got big X-ray scanners there, and they scan lorries as they drive through. Industrial things, lots of processing of heat shrink films and things like that is done with particle accelerators, and obviously our own industry in cancer treatment. So I mentioned the LHC. There it is. I say it's 27 kilometers long, 175 meters underground. I would say 6.5 teravolts compared to our 6 megavolts. So yeah, what's that, 1 million times more powerful? It's a very, very big thing that has enormous energies, and that's the energies they need for investigating these fundamental properties of matter. It says it consumes 120 megawatts of power, 10% of Geneva's entire electricity consumption when they're beam on. It takes quite a lot of energy, and I'm not sure we can really claim that boffins won't destroy the world, not yet anyway, but we didn't with the LHC. So I was saying about synchrotrons versus Linacs. So here's a couple of things for the next LHC that scientists want to build. So you can see this is the size, that's that 27 kilometer LHC. They're talking massive synchrotrons, or this white circle here, that's this big circle. So there's the LHC, which we think of as massive. This is the length of the linear accelerator we'll be talking about as a replacement. So potentially enormous, really enormous tunnels. But you know, we can build tunnels, so maybe that's sensible. But the LHC isn't the end of the road for those for the physicists investigating matter. They still want this bigger one. So I mentioned about light sources. So interesting thing that was found when synchrotrons kind of discovered to have this problem with synchrotron radiation and giving off energy, losing energy. So then everybody's trying to find out, how do we stop it doing that? How do we not lose all this energy? And actually people started saying, well, actually that's quite, we could use that radiation that's coming off. So we started making synchrotrons that deliberately give off this synchrotron radiation, and it's giving it off in the form of light. Now, you see the electromagnetic spectrum, light isn't just the colored bits we can see, but you know, we've got microwaves, radio waves down here, but of interest really is these X-rays, ultraviolet X-rays, hard X-rays. So this is diamond light source in Oxfordshire. If you ever get a chance to go and see it, do. It's incredible engineering. Starts off with the linear accelerator, then goes into a synchrotron and speeds up, and then goes into this big ring where the particles run around. And each of these blue bits here is a research station, and we can use a magnet to kick that that bunch off and get this high energy light diverted into each of these stations. And we can use that light for a number of interesting things. Oh, here's some pictures. Say big round building, and it's all seismically shielded, so there's no vibrations or anything in it. There's the linear accelerator that starts the beam off, and then you can see here's the storage ring around the outside. You see it curving around. So what do you do with a light source? So here's a few projects they've done. So biology, they can use that high energy light to look down to very, very small things, as you see down in DNA itself, looking at viruses. Archaeology, so they've looked within things like not the Dead Sea Scrolls, I think, but things like that, these really old documents that are found. You can't unwrap them because they just fall to dust, but we can penetrate that with the light, and we can go and read what's written inside these documents. Cadbury's did a project at Diamond, I think it was Diamond, looking at chocolate crystals. And it says there's 6 possible crystal forms for chocolate, and there's only one of them that tastes nice. So by doing that project and understanding what that is, they now can force the chocolate to always produce that 5th form of crystal. And you see here a Van Gogh painting. They shone through that and found that it was painted over a portrait. So there's a hidden portrait, Van Gogh portrait of a woman underneath one of his other paintings. So there's a lot of things we can do with this light. It's with its penetrative properties. So I mentioned industrial uses. So irradiation for sterilization is a major use of accelerators. So most medical products get irradiated to sterilize them. We can use it, as it says here, this detecting wine fraud. It does other things as well, but we can look at a signature from putting radiation through it, and we can prove whether or not it's the real thing. Shrink films, let's say, so like heat shrink tubing, shrink films, ink curing, they're all kind of done with radiation from accelerators. And it says topaz and other gems like that are quite often artificially coloured with the radiation. So you can get relatively cheap stones out of the ground and turn them into much more expensive stones than finding the real good quality ones. And cargo scanning, as I said, so they scan within vehicles. This picture on the right, that's from my dash cam at Calais Eurotunnel. If you get pulled over and have to go through the scanner, you get out the car and it drags it through here, and that's an accelerator giving X-rays to scan your car. Interestingly, we all thought that was going to be, with all this cargo scanning of lorries, that they'd be looking for migrants or weapons or drugs, and what they're really looking for is alcohol and tobacco, because that's where they make all the money on import duties. So that's mostly what they're looking for, and we know how much certain materials absorb X-rays, so they can make these scanners that sort of highlight things that are the right density for tobacco and for alcohol. So that's kind of what they're used for in industry, which brings us to what we use them for, which is to treat cancer. So what is cancer? Very briefly, is you get an error in the genetic makeup of cells, either from, lots of things can cause that. Can be genetic, can be external things like chemicals or radiation. All sorts of things can cause that fault to happen, and those cells then multiply and just keep multiplying. They don't stop multiplying, and eventually bits can break off that tumor, and they can spread around the body in the bloodstream or the lymph system, and then they make new tumors, and then you end up with this spread of cancer within the body. So there's a lot of cancer in the world, sadly, as you see here, and it is increasing. So lots and lots of cancer around the world. See here, so most common cancer in women is breast. This is a global. This is a bit old. Say this is 2012. It's 10 years old, but 1.7 million breast cancer cases globally per year. That's a lot of cancer. And for men, lung is still the biggest, but that is reducing globally as fewer people smoke. But prostate, as you see, is not far behind. That's still a lot of cases, millions of cases around the world. So there's a lot of people get cancer and need to be treated. And how do you treat cancer? Well, we moved on a bit since that 1938 poster, but the majority is still surgery or chemotherapy. Everybody's heard of chemotherapy, where they give you drugs and you lose your hair and feel really ill, but it kills off the cancer. But actually, the majority of cancer treatments are radiotherapy, using radiation to treat the tumor, and that radiation is almost always generated from a particle accelerator. So what is radiotherapy? So yeah, we use radiation, and we're usually using X-rays, not always, but usually. And those X-rays damage the DNA. Now, it damages the DNA of the tumor. It also damages the DNA of normal cells. The big difference is healthy cells have an immune response and they can recover from the injury we give them from the radiation. Cancer cells can't. So cancer cells die off and healthy cells recover. So this is what we try and do, is we give this treatment in a number of what we call fractions. So it's not a massive dose of radiation to burn the tumor out of the patient. We hit the tumor with enough radiation, but we're also hitting healthy tissue. And then you'll come back the next day and have it again, and the next day and have it again. And that could be 20 or 30 fractions. You have to keep coming back to be treated. And each time you do that, as we see here, if we give a treatment, the health of the cells drops, then you'll have maybe a day off, and in that time your healthy cells will recover, but the tumor cells won't. And then you take another fraction, you drop down, the healthy cells recover, the tumor cells don't. And over time, say maybe 20, 30 fractions, the tumor shrinks as these cancer cells die off and your healthy cells survive. And then hopefully at the end of the treatment, there's no tumor left to be seen while your healthy cells are back to full health. So it's a horrible picture of early radiotherapy machines. So this is before accelerators, and these were, it says Radium and Cobalt machines. So inside this part of the machine here is radioactive material, radium or cobalt, and that is emitting gamma rays constantly. And you have to have big pieces of lead in there to absorb the rays when you don't want them. It's a very simple system. It's shooting a round beam of radiation through the patient. The one sort of good feature about it, as you can kind of see, is it's on a gimbal here, so this whole thing can rotate around the patient, so we can shoot beams from different angles. That's quite important to concentrate the radiation on the tumor. So I said our first Linac was 53, so sort of 50s, 60s, we have these early accelerator-based machines. Once again, it's all horrific death ray kind of Dr. Strangelove machinery. This little boy here had a tumor in his eye and was treated on this machine and kept his sight and lived to a very old age, I believe. So he's one of the first very successful treatments with accelerators. I think, judging from the size of these would be those electrostatic accelerators or Cockcroft-Walton kind. So before the cavity Linacs as we see them today, RF-driven Linacs, which is what we start getting to here. So this is one of our machines from the late 60s, early 70s. And we have a cavity linear accelerator in there, and then bend the radiation beam. The radiation comes out here, and like those early machines, it's now small enough that we can make the thing rotate so that we can shoot the radiation beam from all around the patient. And that's important because, as you see here, you've got the tumor. If you just shoot a beam straight through, you're giving as much radiation to the healthy tissue in front and behind as to the tumor. If you shoot from all these different angles, what you get is a concentrated radiation dose in the tumor and a dispersed, lower intensity radiation dose to the rest of the body. So this is traditional radiotherapy treatment. You shoot from all these different angles and do that as one fraction, then come back tomorrow or the day after for another fraction, and slowly the tumor shrinks down. Big advance in the sort of 1980s is the Multileaf Collimator, the MLC. I think I've got a little video here. don't know if the sound came through there, but basically each one of these leaves here, as we call them, they're made of tungsten. It's about 18 tons per cubic meter. It's very, very dense metal, and each one is powered and can move in and out of the radiation beam. So we can form shapes like this on the right. We can form the shape of the tumor, and then rather than just shooting a round or a square beam through the patient, we are only shooting the shape of the tumor, and then we rotate, change the shape again, and shoot through. So that was a big advance in the sort of the 1980s and early 90s to do this more conformal therapy. So we're giving less dose to the healthy tissue. As we touch on treatment planning, this is the big advance really in the last 10 years or so, is more advanced treatment planning with faster and faster computers. So this thing here, this blue bit here, GTV, this is the gross treatment volume. This is what the doctor says we've got to give the radiation to. Then we've got the CTV, which is the clinical treatment volume. Now, we've got uncertainty on this. So we've seen it, the doctor's seen it on the CT scan or the MR and said, that's where I want to give the radiation to. But say there's some uncertainty on that imaging. So we have to treat a little bit bigger than that to be sure that there's no little sort of tendrils of the tumor coming out that we couldn't see on the image. And then we got the big one, the red one, the PTV, that's the planning treatment volume. And that's bigger again because we have uncertainties on position. So especially something like a lung tumor that's moving as you breathe, that could be all over the place. So to be sure of hitting that tumor, we have to have a really big volume we give the radiation to. And the problem with that is we're giving all that radiation to healthy tissue as well, and we don't want to do that. So this funny image on the right here, you can see where these blue beams coming in. These are the radiation beams coming in from different gantry angles, and you can see the high intensity radiation doses building up here where we want to give it. But that planning treatment volume is important, and we'll come in a couple of slides time to how we've improved the outcomes for patients using these better treatment planning techniques. So we'll look at our standard accelerator. I've got another video, I think, so hopefully you're getting the sound. Ooh, sorry. So hopefully you got the sound there, but as you saw, our accelerator actually is sort of diagonal within this arm. And as we explained before, we inject microwaves at one end, and those electrons surf along, going faster and faster with each cavity they go through. And then we bend it around the end here. And then this is that multi-leaf collimator I was talking about. So that's where all those tungsten leaves are moving in and out of the beam, so that we end up shooting a beam of the right shape and the right intensity to where the tumor is. And this whole thing, as you can see, it's got this polished rim and it's sitting on these wheels. That whole thing can rotate. And this is what it looks like with its covers on. So hopefully you never have to see one of these in the flesh. But if you do, that's sort of what they look like. They're big and they rotate around. These extra arms, come to in a moment, but what they're all about. So there it is in our factory with all the covers off. Yeah, big rotating steel structure. The whole thing's about 6.5 tons, and it's all balanced to the center so that it sits on these wheels and can rotate around with really a very small motor. But everything's on there. We've got all of that magnetron microwave generation is on there. The accelerator itself is on there, and all the control systems and everything to make it work. So here's that accelerator that's within our standard thing, 2.4 meters long. You say 18 to 25 top energy, which in medical that's pretty high energy. So you compare it to the big atom smashers, and it's absolutely nothing. But yeah, that's all you need. Don't even really need that with modern techniques in radiotherapy. And here's some cross sections through the accelerator. So this is what I was saying about these cavities. See them in here. So the bunch of electrons comes through, enters this cavity, and picks up on the wave and surfs its way through. And each time it goes from cavity to cavity, it gets another push. So from an engineering point of view, here's sort of how we make it. So it's made in individual cells. So you see these cells on the left, and they're diamond turned to a mirror finish in very pure copper. In order to push this electron beam through, the whole thing needs to be under quite high vacuum. So if there's any air molecules inside there, then the electrons are going to hit them, and then they don't come out at the end. So the whole thing has to be ultra clean. The material has to be ultra pure, and it takes us quite a lot of processing to get it to that level of vacuum. So we produce these cells on a diamond turning lathe, and then they're all stacked up together with these bits on the right, which is braze wire. And then we put the whole thing in a hydrogen furnace and take it up to temperature and melt the braze. And that runs in all the gaps by capillary action, and then we cool it down, and then we've got a single structure. And then we can go and process it and put it into the machine. So here's them after they've been in that hydrogen furnace. They're beautiful and shiny. So that's why we use the hydrogen. So any oxygen that's inside the copper, you know, we say it's oxygen-free copper, but there's always going to be a few molecules of oxygen in there. They bond with the hydrogen at temperature and form steam and are pulled away. So all that sort of tarnished copper is from oxygen. So when we put it in with the hydrogen, what we get out of these beautiful shiny structures. It shouldn't really be this color on the right. That's from a failed guide. I thought it was useful to show you again those cavities and how it's becomes a single structure. You can see the lines here where the joins are, but it becomes just a single big copper structure. And just to put that into perspective, we said about the 27-kilometer long Large Hadron Collider. Yeah, we have right now about 5,000 of our systems in the world, which is just under half the length. So we're quite proud of that. That's quite a lot of accelerators. So if you were unlucky enough to have to visit a radiotherapy machine, the state of the art, I guess, is what we call VMAT, volumetrically modulated arc therapy, which is they love using very long words. But I mentioned before about we shoot from different angles. So this is conformal therapy. So if the tumor's this funny shape, traditionally you would have just had a square shape shot through from one side and then from the other, and that's what you got, and that would have killed off lots of healthy things that we didn't want to. In the sort of 2000s, we moved to intensity-modulated radiotherapy, which is a lot more angles, but also more control over the shapes because of those new then multi-leaf collimators. So we can now start conforming the shape much closer to the tumor, which means we can give more radiation to the tumor and less to the healthy cells. And VMAT, as I say, is kind of state of the art. This is, instead of taking individual shots at different gantry angles, we are rotating around the patient in a continuous fashion with the radiation on, while modulating the shape of those MLC leaves. And that allows us, as you can see there, to really not blur it out, but to conform the dose to the tumor very closely while minimizing the radiation dose to the healthy cells. So that's been a revolution in the last sort of 20 years, and radiotherapy outcomes are now much better than they were in the 80s or before. The other big thing we brought in early 2000s is image-guided radiotherapy. This is where I said about those other arms. So the extra arms there are a CT scanner, effectively. So we can rotate around the patient before treatment like this with the CT scanner, and we can actually see where the tumor is within the patient just before treatment. And then we can use a 6 degree of freedom table to adjust the position of the patient in all six degrees, so that the tumor is back where we thought it was from the planning scan. So that way, if you've had lunch today and when you had your scan you hadn't, and your stomach is now bigger, the tumor might have moved over. But we can tell that beforehand now, and that means we can reduce that big red shape, that planning treatment volume. We can reduce the size of that, which once again, if we can conform better to the tumor, we can put more radiation in the tumor, less in the healthy cells. That means you're going to have fewer fractions and you're going to have better outcomes. So this is, once again, from a software point of view, this is a big advance, but the hardware involved in that was quite a project as well, having this additional lower energy X-ray system added onto. So this is quite common now in hospitals, using this image guidance immediately before the treatment. But while you're actually being treated, we still can't see anything. That's quite important. We're lining everything up before treatment and then keeping you in the same place. So the last thing, come on to a couple of things you might have heard in the news quite often when you hear of some poor patient who's very sick and needs a specialist treatment. Sometimes makes the news about proton therapy. So proton therapy, I said we accelerate these subatomic particles, and it's usually electrons or protons. Protons are a lot more massive than electrons, so they're much harder to accelerate. But the beauty of them is our normal radiotherapy is like this pink beam here. The dose carries on through the patient, which you kind of know from when you go for an X-ray. The X-ray travels through your body. That's how it works. So when we're treating with X-rays, we have to do all that VMAT and IMRT. We have to do fancy stuff to reduce the dose to the healthy tissue. The beauty with protons is we have this thing called the Bragg peak, and that means as the protons go into the patient, you get this peak, and then you don't get any more dose or energy deposited after this depth. And you can move that depth by changing the energy, so how much you accelerate. So as well as doing as we do in traditional radiotherapy of shaping the beam and choosing which angles to come from, in proton therapy, you can also stop the beam from traveling any further. So particularly in brain treatments, this is really important. There's lots of things in the skull you don't want to give radiation to, like the eyes, obviously, and the brainstem. They're very easily damaged with radiation. So proton therapy is perfect for this, because nothing is as good at controlling exactly where the dose is given. So why don't we use proton therapy for everything? Well, there's a couple of reasons. The main one really is cost. As it says, the proton systems have been described as the most expensive medical device ever built. They are expensive. So it says they're $225 million each. A normal Linac of the kind we make is in the order of, you know, 1 million, shall we say. I'm not a salesman, I don't know exactly, but you know, we're not in the hundreds of millions for sure. So they have to be used for the things they really need to be used for. They're not really a system for run-of-the-mill treatments. So they are. We have a few systems in the UK now, in the last few years, and they are used for these very complicated tumours, particularly in the head, and for children, because without meaning to sound crass, if you're in your 90s with cancer and we cure that cancer, you're probably going to die of something else fairly soon. If you're a child, you've got a whole life left to live. So it's very important that we make sure there's no radiation going to the wrong place. So they're very expensive, but also a problem with protons is what I said about traditional radiotherapy. We can image the patient immediately before treatment, but we can't image them during treatment. Now, in the head, that's fine because it's kind of bony and nothing's moving around. But if you want to treat a moving lung tumor, or you want to treat anything sort of in the belly area, so pancreas or bowel cancer or something like this, that's all kind of jelly. That's all moving around and squidgy. Imaging immediately before treatment isn't that much use sometimes because it might have moved during the treatment. So especially imagine a lung tumor while you're breathing, it's moving a lot. And that's where the MRI Linac combination comes in, which our new product, Elekta Unity, that we launched a few years ago, combines an MRI scanner and a linear accelerator together. The beauty of that, apart from the MRI being a better imaging device, we can see those images from the MRI device while we're treating. So it opens a whole new world now. The surgeon's effectively taken his blindfold off and can actually see while we have the radiation beam on. So the MRI is excellent at seeing soft tissue, which is what tumors are, whereas X-rays aren't that great for that. And it's at the time of treatment. That's really important. So you can see here, sort of top left, while you're breathing, you see how much movement there is of your organs. So if you're treating a tumor on somewhere like that, how are you going to manage that? Well, the only way you manage it is with that big red planning treatment volume. You give radiation to the whole area it could be, which means lots of damage, which means you have to use lots of fractions. But now with the MRI Linac, we can see where it is, and we can see where it is in real time. So the goal, we're not there yet with the software, but the goal of MRI Linac from everybody in that field is to be able to see this tumor moving in real time and then use that to follow the radiation beam with it. So we're not quite there yet. That's future, but that's the dream that MRI Linac can open up. So we don't have the dose distribution as that beautiful distribution from the protons, but we can see what we're shooting at, and that's really important in these soft tissue tumors in the body. This is a little complicated to understand, this thing, but imagine this is the target we're trying to shoot the radiation at, and right next to it you've got something we really don't want to give any radiation to, so like the spinal cord, for example. But because of the uncertainty where that target is, we have to have this big planning treatment volume we have to give radiation to, and that means we're going to be giving radiation to this healthy tissue that we really don't want to do. So you see that's right in there. And if you use protons, well, that's great. That's going to give you a better curve, but it's still got to be through that healthy tissue because you've got to irradiate this whole thing. With an MRI Linac, we know where the target is, which means we can make our planning treatment volume smaller, which means we can move in closer, which means we can avoid that healthy tissue. So that's the thing. It allows us, it removes the uncertainty on the position of the tumor, which means we can give radiation, more radiation to that tumor. From an engineering and physics point of view, the problem why nobody did an MRI Linac for decades is, you probably know, MRIs have giant magnets. They kind of need them to work. They need a giant magnet, and electron beams are steered by little magnets. So this is the same picture we saw before of the electrons being accelerated. But if you put even a small magnetic field on it, you kind of see there's not a lot coming out at the end here anymore. It's all splashing off to the sides from that small magnetic field. And this is a field of, I can't remember, something like 10 or 20 Gauss. An MRI imager, the kind we use, is 1.5 Tesla. That's 15,000 Gauss. So, you know, if we did nothing, if you put a particle accelerator next to an MRI, nothing comes out. And the way we solve that is by bending the magnetic fields. So you see these orange bits here, these are the magnetic field lines, and you kind of see they're bent around the accelerator. So even though the accelerator is right next to that giant magnet, it doesn't get, it doesn't see that magnetic field. So that allows us to run the two systems next to each other. So there's a couple of pictures here. It's a bit dated now, 2016. This was one of our first prototypes at the Royal Marsden in Sutton. We have another one in the UK up at the Christie in Manchester, and that was the installation. And there's Sadiq Khan at the opening of it in say in 2016. It looks a bit nicer than this now. This was a prototype system. It's been upgraded a bit since then. And we have around 50 systems clinically operating, treating people as we speak around the world at the moment, growing rapidly. And this is the big thing. We can forget a lot of this. It's by being able to focus in on the tumor much closer means we can give more dose to the tumor, which means we can reduce the number of fractions. And it says here more than 50% of the treatments on these machines is 10 fractions or less. The goal, and there are research sites out there doing it, traditionally a prostate treatment is going to be 20 to 30 fractions. There are people out there now with Elekta Unity treating in a single fraction. So that's the goal again. You know, the sort of science fiction future we're working towards is you get diagnosed in the morning and you go and get on this machine in the afternoon, and then you go home and it's done. We're not there yet, but that's where we're aiming towards. So that's kind of the end of that. As I say, some summary wise, yeah, accelerators have been around a long time, but there's still a lot of research, still a lot of improvements and advancements, and some really interesting ideas coming out all the time. And from a cancer point of view, cancer is growing. More people are getting cancer, but Linacs are the primary tool for treating cancer. And the advancements we're making in our industry has radically changed outcomes for these cancer types that we treat. And final slide. So in the hour I've just been talking, about 15,000 patients have been treated by one of our systems. So I'm quite proud of that. And that's it. Thank you very much.